So our new unit is on exponents and logarithms, okay? So exponents, I know you guys have done on before. And that second word I said, logarithms, you guys aren't really familiar with. So this will be your first kind of look into logarithms. Not this first section, it's gonna come a little bit later. Logarithms are often confusing to people. But I think that a lot of teachers don't explain them very well. So when we get to the logarithms, I will do my best to explain them. I think better than most teachers. So let's hold that thought. Let's focus on the exponents for now. Like I said, it's something you're kind of more used to here. Okay, and so the first thing we're going to start off with here today is writing an exponential function that the data in the table represents, okay? And this is gonna be kind of our key here, formula, y equals a times b to the power of x. And what we really need to find is, we need to find a and b, okay? So I put them kind of backwards here because usually we're gonna find b first, all right? And so b is the growth rate, and it's a multiplier. So it's kind of like, what am I multiplying as I go along this list, okay? That's what we call the growth rate. And then A is the Y value when X is 0, okay? So let's just take a look here at number 1. And so how I kind of do this is I notice my X values are increasing by 1, and I just think to myself, well, what's multiplying as I go from 9 to 27? Okay, does anybody know what's multiplying as we go from 9 to 27? What do I have to multiply by?
3.
3, very good. Okay, so I'm just gonna put times 3 here, okay? Does that pattern continue here to get from 27 to 81? Yes, that is times 3 again. And then the last one here from 81 to 243, you could double check that on a calculator, but I will tell you that that is times 3 again. So our multiplier is consistently 3. So I'm going to say that b on this one, number 1, equals 3. Not too difficult, right? Okay. Now, a is the y value when x is 0. And so it doesn't tell me what the y value is when x is 0 here, correct? So what I have to kind of do then is, how would I show this? I would kind of show it like this. So you know what I'm going to do? I'm going to make the XY table kind of like this. So I'm just going to kind of flip this table, okay? And I'm also going to put 0 and 1 there. Now we know that when x is 2, y is 9, correct? And we know that when x is 3, y is 27. That was given to us on the table, right? And so what I need to kind of think about is, well, what would these numbers in the front here be, okay? So if I go backwards here, well, we said it was multiplying by 3 going forwards, correct? So it kind of makes sense to me that if I go backwards, it's actually dividing by 3. So I could divide by 3 if I want to go backwards here. And then I could divide by 3 again. So I got when x is 0, y is 1. And so that tells me that a is 1. Okay, so my equation here is going to be y equals 1 times 3 to the power of x. Or we know that multiplying by 1 doesn't really change anything. So if your a is 1, then it's allowed to be invisible. Only if a is 1, though. Okay, let's try our next one. So what do I have to multiply to go from 25 to 125?
5.
Yeah, this one is times 5. So then I know B is 5. So then I know if I build my table, since I'm going multiplying by 5 going forward, I'd be dividing by 5 going backwards. So that one would be 5. And that one would be 1. So A is 1 again. So I could say y equals, I'm just going to say 5 to the power of x. So anytime A is 1, I'm going to go ahead and make it invisible. All right. Yeah, let's do one more. We'll skip number 4, but we'll do number 3. So this one, I see that our multiplier is times 2. This one, we're gonna have to go all the way out to 4 and 5 because that's our known values. So we know the y value at 4 is 16 and the y value at 5 is 32. So we'll divide by 2 going backwards. You get 8. Keep dividing by 2. And A is 1 again. I think actually I made it so all of these A is 1. I wish I wouldn't have done that, but that's all right. Okay, so that is that. The other thing we're going to do on this unit, or sorry, in this section, is we're going to solve these exponential equations, okay? So we'll go ahead and skip number 4. Let's jump down and do number 5. So a little bit different instructions here. We're solving equations. So the big thing I want to get across here is the idea of balance, okay? Balance, okay? So just a sec. Okay. Equation means like this side should balance out with that side, right? They need to be the same on each side. Well, if we look at the big number, which I'm going to call the base, okay? The base is kind of the big number that holds up the exponent. That's the name for that, is the base. And I'm going to start using that word more here because it's going to help us later on. So the base here, you can see, is 2, right? This base is 2. This base is 2. All right. Does 2 equal 2? Yes, definitely. Correct. That part is equal. So if that means that since the bases are the same on each side of the equal sign, if I want this to be a true equal equation, I just need the exponents to equal each other, right? So if you have bases that are the same, you can just make their exponents equal to each other. And if you can solve that, that's going to make your equation balanced, all right? Now, what if your bases are not the same on each side? Hold that thought. We will get to that today, actually. But for now, you can see on these first 4 questions, the bases are all the same. So if the bases are the same, set the exponents equal to each other. So now we'll add 1 over here. So 3x equals 5. So x equals 5 over 3. Done. All right, same idea with number 6. We see the bases are the same there. So we can just set the exponents equal to each other, and we're just going to solve that, and that's all we need to solve here. I got 7 over -2. Usually when they have a negative on the bottom of a fraction, they just throw that in front of the fraction. So they're saying the whole fraction is negative, right? If you did put it down there with a 2, that's fine. But on multiple choices, they're going to put the negative in front of the fraction, okay? All right, so then same idea with number 7 and 8 here. Now they're going to take a little bit of a left turn in a minute, but the first step's the same. The bases are the same. When the bases are the same, we just set the exponents equal to each other. Now, in this case, I have variables on both sides of the equation now. Whenever you have variables on both sides of the equation, you want to get them all on the same side. So I'm going to add, not 3x, excuse me. We'll add 3v over to the right side. But it's kind of a special case here because you can see it cancels out on both sides and it says 0 equals -3. So our variable is gone now. It says 0 equals -3. Thinking back to our last unit, does anybody have an idea? Anybody have a guess as to what I'm going to write down here for this one? What was it? No solution is correct. We said that last unit when we did those systems of equations. When your variables cancel out, right, and it's left you with something that's not true, then that means no solution. So there's no number that I could put in there for v in the original equation that would make those two sides balanced. It's not possible. Some questions in life have no solution, correct? Like if I said, name a state in the United States that starts with the letter X. You have to say no solution, right? Because there are none. You know what I'm saying? Okay. Let's try the next one. So on the next one here, what color are we going to do? We'll do a little orange. Okay, so we have the bases are the same. So it says -3x equals -3x. I would add the 3x over here, and it would say 0 equals 0. So we see our variables cancel out again. And so, thinking back to last unit, what do you think we're going to write for this? Infinitely many solutions. Very good. Or we could just put infinite solutions. And that actually makes sense in this case. If you look back to that original question, it's like, when does 9 to the -3x equal 9 to the -3x? Like, those things were already the same anyway, right? So obviously this one is infinite solutions because it's like asking you for what values of x do these things equal each other? Well, it's like all of them, right? Because that's literally the same thing on each side of the equation anyway. Okay. Awesome. So now let's go on to the next page here, and it's going to get a little tougher, okay? Because now you can see that it's not the same thing on each side of the equation, okay? It's not the same base, I should say. So this one's a base of 4, and this one's a base of 16, all right? So we still need to solve it. So how are we going to solve it when the bases on the bases are not the same on each side of the equation? Well, the answer is we're going to make them the same, okay? We're going to make them have the same base. So we have to look at these two bases here, and we're usually going to look at the bigger one first, and you're going to think, can I write 16 using a base 4? Okay, can I write 16 using a base 4? And I'm going to say yes. 16 is 4 to what power? 2. 4 to the second power, correct? 4 squared is 16. So I'm going to rewrite 16 as 4 squared. Did I really change it? No, right? 16 is 4 squared. I just rewrote it. Why did I rewrite it? Because I wanted them to have the same base. Now that they have the same base, what can I do? I can set the exponents equal to each other and solve. Look at that. Now it turns into those ones we saw before. So I'm going to subtract the 1 over. Divide by -3. And x is going to equal -1/3. Okay. All right, now let's try out number 10. Same idea here. So I'm going to start off, I'm going to look at the bigger number. So the bigger number is 16. Can I write 16 as 2 to some power? I think yes, okay? So I'll count this one out. So 2 to the first power is 2, right? 2 to the second power, 4. 2 to the third power is 8. 2 to the fourth power is 16. So if I multiply 2 by itself 4 times, it's going to give me 16. So it's going to say 2 to the fourth equals 2 to the -n. Are you allowed to check on a calculator if 2 to the fourth power gives you 16? Of course, yes, right? And what if you're not sure what the number is? Can you try out a couple different things on the calculator? Yeah, you could try, well, it's 2 to the third. It'd be like, oh, it's 8. Okay, let's try 2 to the fourth. Oh, that's 16. Got it. All right. You are allowed to use calculators in this class, right? You can use decimals.com if you don't have your own calculator, so please do. Okay, so what do we got here? Now we can get rid of the bases and just set the exponents equal to each other. So we have -n equals 4. I would divide both sides by -1, and that gives me n equals -4. Okay, not too bad, right? All right, it's going to get a little trickier here on these next two questions, so stick with me, pay attention. I'm going to explain it. I'm going to give us a second to get caught up here. And I really want to explain numbers 11 and 12. Okay, so number 11. We got 3 to the 2x equals 1 over 27. That's kind of a weird one, right? Okay. What's the bigger number? Well, actually 3 is technically the bigger number because it's 1 over 27, but let's pretend that 1 over wasn't there for a second. Let's just pretend it was 27, okay? Can we write 27 using 3 to some power? The answer is yes. 3 to the third power is actually 27, okay? So I can first kind of adjust this like this. I can say 3 to the 2x equals 1 over 3 to the third, right? That would be keeping it the same. We know that 3 to the third power is 27, right? And you could verify that on a calculator. So right now I've just turned that 27 where it was into a 3 to the third power. However, I don't like this the way it is right now because it's in the denominator, right? Like it's in a fraction. I don't want that, okay? So how do I write this one without it being in the denominator? Well, there is actually a way to do this. Here's how we do that. If you have kind of the base you want, but it's in the denominator, you can write it just normally if you make that exponent negative. Negative exponents move stuff from the numerator to the denominator or vice versa. We did talk about this a few units ago where I always told you guys, if you have a negative exponent on bottom, move it to the top. If you have a negative exponent on top, move it to the bottom, correct? So this negative third power here really means 1 over 3 to the third. However, I want it like this because now I have my bases the same. You see how I did that? So I have both bases of 3. 3 to the 2x equals 3 to the negative third. So now that I've made my bases the same, and this one was definitely trickier than the ones we saw before, now though, I can get rid of the bases and set the exponents equal to each other. So I'm going to divide both sides by 2. And we get x equals negative 3 over 2. Okay, so that one was definitely trickier. I don't know if we're going to be seeing a ton of those fraction ones. Do we have any more? Yeah, we do have one more. So we'll practice it again down there, okay? All right, number 12 is a little different for a different reason. So let's check out number 12 now. So number 12, I got 81 and I have 27. All right. So I look at the bigger number, I look at 81, and can I write 81 as 27 to some power? Well, 27 squared is going to be a big number. Let me look it up. I'm going to do it on my watch, actually. 27 times 27 is already 273. So that's already too big, right? Wait a minute. I don't even think that's right. Excuse me. It's got to be way bigger than that. It's got to be some thousands. Oh, no, not quite. 729. Either way, it's not 81. You know what I'm saying? So like this fact is not going to work for me. I can't do 27 to the first power, right? Because that's just 27. That's not going to turn into 81. I can't do 27 to the second power because that's too big. It's somewhere in between 1 and 2, okay? But I'm not going to think about what that is because that's too tough. Here's what I'm going to do instead. Can I change both of these to the same base? Is there some base that I can write both of these as? And that's going to be a yes, okay? The base is 3. So I'm actually going to write both of these as a base 3. So 27 is 3 to the third power. 81 is 3 to the fourth power. So sometimes, instead of just changing one of the bases, you're going to have to change them both to a common base. That base is usually going to be probably a lot smaller than both of the bases, okay? So we can get them both with the same base. So 27, I have 3 to the third power. 81, I have 3 to the fourth power. Now you'll notice here that wherever the variable was, I keep it in the same spot, but it's kind of outside parentheses here, all right? Because if we're thinking of the 81 is turning into 3 to the fourth power, that p is still going to be outside of that. Now, our rule for this, when you have one exponent with 2 different powers, is you actually multiply those powers, okay? So I'm going to multiply 4 times p, which is, of course, 4p. Now, finally, and this one did take a little bit longer, I have the same base on each side. So that means I can actually get rid of the bases and just set the exponents equal. P equals 3 over 4. Okay, so number 13 is going to be kind of similar there to number 12 that we just did. Okay, so let's try this one out. So I got 8 and I got 4. Once again, I'll look at the bigger one, 8. Can I write 8 as 4 to some power? I'm going to say no. 4 squared is 16, right? It's already too big. So I'm going to have to rewrite both of these, okay? So what base can I write both of these in? Well, it's got to be smaller than both of them. I think that base has to be 2, right? So I know 8 is 2 to the third. And that has the x plus 2 on the outside. I know 4 is 2 squared, and that also has an x plus 2 on the outside. So once again, we kind of have a base with an exponent on the inside of parentheses and another exponent on the outside of parentheses. And in these cases, we always multiply those exponents together. So I'm going to do that now. But now it's multiplying by x plus 2. That means it needs to distribute. So I'm going to distribute that in there. So I get 3x plus 6 is my new exponent over here. And then over here, I need to distribute as well. So I get 2x plus 4. All right, I have now made my bases the same. So now I'm ready to get rid of the bases and set the exponents equal. So we have 3x plus 6 equals 2x plus 4. So now we need to solve that. I have variables on each side of the equation. So in that case, we always want to move all the variables to the same side. So I'm going to subtract the 2x over here. Finally, I'm going to subtract 6. So I get x equals -2. Okay, I think we only have time for one more. So I would really like to do number 15. So we're going to do that as our last one, okay? I'm going to go ahead and write down here. If you'd like to do 14 or 16 on your own, feel free. If you'd like some extra practice, I'll tell you on number 14, let me give you the answer. It's -13 over 5 if you'd like to do it on your own. Oh, And on number 16, A is -1 over 6 if you'd like to try that one out. All right, but let's focus on number 15. That's really what I want to get done here. Let me grab a good color. Let's go blue. Blue for UCLA, my college I went to, who won their tournament game, and they got another tournament game today. So hopefully they win again. All right. All right, so we got 81, and our other base is technically 1 over 3, okay? And I'm gonna kind of mark this as 1 over 3 to the first. And so we have that fraction again, right? And so I have 1 over 3 to the first. And so I can always write that without being in the denominator if I just make it negative. So I'm gonna do that. I'm gonna write it as 3 to the -1 power. So that's how we're going to be dealing with fractions, is with a negative exponent. You can write it as just a regular number there. So my base is 3. Can I write 81 with a base of 3? Yes, I can. I think we did that earlier, right? 81 is 3 to the 4th power. So I'm going to rewrite this one as 3 to the 4th power on the inside of parentheses, and then 3x minus 3 on the outside. The 3x minus 3 was kind of already there, and then I just rewrote 81 on the inside as 3 to the 4th power. So you are going to need to multiply those exponents on the left side. So we're going to distribute the 4 into the 3x minus 3. So that's going to become 12x minus 12. We now have our bases are the same, so we can set the exponents equal. So I can get 12x minus 12 equals -1. Add the 12 over. Divide by the other 12. X equals 11 over 12. Beautiful.